The end-to-end argument fate sharing. When a large system such as an operating system or protocol suite are being designed, a question often arises as to where a particular feature or function should be placed. One of the most important principles that influence the design of the TCP or IP suite is called the end-to-end argument. So it basically works or revolve around this sentence. The function in question can completely and correctly be implemented only with the knowledge and help of the application standing at the endpoints of the communication system. Therefore, providing that question function as a feature of the communication itself is not possible. Sometimes an incomplete version of the function provided by the communication system may be useful as a performance enhancement. So this is what we said when we talk about how we provide the features, but by default we don't provide all the advanced feature. It's up to the application to implement that itself. It argues that correctness and completeness can be achieved by involving the application or ultimate user of the communication system. Efforts to correctly implement what the application is likely to need are doomed to incompleteness. In short, this principle argues that important functions like error control, encryption, delivery acknowledgement should usually not be implemented at low levels for layers, link layer, physical layer, network layer. It could be applied by the application depending on how it will configure its transport, but by default, the the transport layer should leave that to itself, to the end user or end host. However, low levels may provide capabilities that make the job of the endpoint somewhat easier and consequently may improve performance. The end-to-end argument tends to support a design with a dumb network and a smart system connected to the network. So this actually support the design of a dumb network, meaning the network doesn't know anything and a smart system's connected to the network. So a smart system could be an application activating some feature of that dumb network, advanced feature of that dumb network that made it smart. This is what we see in TCP or IP design, where many functions like methods to ensure that data is not lost, controlling the rate at which sender sends, are implemented in the end host where the end application reside, because the application could choose to implement it. The selection of which functions are implemented together in the same computer or network or software stack is the subject of another related principle known as fate sharing. So fate sharing talks about how the function or related function in the same network will be grouped. Fate sharing suggests placing all the necessary state to maintain an active communication, association, or virtual connection at the same location with the communicating endpoints. Because they have the same related function in the network, the communication to them must not be cut off. Kind of like the functions placing together in a front end in design that we discussed in the previous video. With this reasoning, the only type of failure that destroys communication is one that also destroys one or more of the endpoints, which obviously destroys the overall communication anyhow. Now, because of this, because one application could still access to other application in this maintain connection or maintain state network, The only way for you to destroy all this communication is by destroying all the computer in the network. Fate sharing is one of the design philosophies that allow virtual connections, like those implemented by TCP. To remain active even if connectivity within the network has failed for a modest period of time. Because of these computers or network sharing on active connection, despite a loss of connection of other networks, it's still connected. So that's what we call fate sharing. So TCP implements that. That's why even though you lost your connection for a bit, you're still able to uh, get back to the other host in this modern internet. Error control and flow control. There are some circumstances where data within a network gets damaged or lost. This can be for a variety of reasons, such as hardware problems, radiation that modifies bits while being transmitted, being out of range in a wireless network, and other factors. Dealing with such errors is called error control, and it can be implemented in the systems constituting the network infrastructure or in the system that attach to the network, or some combination. So a lot of things that can happen that could damage the data or the packets, like a hardware problem, the actual device sending it, the network card inside that, the radiation that modifies the bits along the link layer and physical layer while being transmitted, being out of range in a wireless network. So the network is out of range from your network, could be a reason as well. Dealing with such error is called error control, and it can be implemented in the systems constituting the network infrastructure, or in the systems that attach to network, or some combination. So a strategy could be an error control attached to outside, from outside network, or inside the network, or a hybrid. Naturally, the end-to-end argument and fate sharing would suggest that error control be implemented close to or within application. So if we use that fate sharing concept, we want to be able to put the error control close or within the application. So the key is close or within. Usually, if a small number of bit errors are of concern, a number of mathematical codes can be used to detect and repair the bit errors. When the data is received or while it is in transit, this task is routinely performed within the network. So again, usually if a small number of bit errors, because remember the packets is just a bit from memory of that sending host. Number of mathematical codes can be used to detect and repair that if it's only small when data is received or while in transit to the end host. So this task is performed within the network instead of outside. When more severe damage occurs in a packet network, entire packets are usually resent or retransmitted. So if it's more than that bit of an error of the packet, a retransmission or resending must be required. In circuit switch or VC switch networks such as X.25, retransmission tends to be done inside the network. So the X25 or virtual circuit we discussed in the previous video, it is being done via retransmission inside the network instead of outside. This may work well for applications that require strict in-order, error-free delivery of their data, but some applications do not require this capability and do not wish to pay the cost, such as connection establishment and potential retransmission delay to have their data reliably delivered. So if you want a strict in order or error-free delivery, kind of like a TCP, you may want to use this type of error control within the network, because instead of like using mathematical code, you're doing retransmission. If you want to avoid that retransmission delay, if you want the others to consider or to acknowledge it, you're using UDP. You don't need this. Even a reliable file transfer application does not really care in what order the chunks of file data are delivered, provided it eventually satisfies that all chunks are delivered without errors and can be reassembled back into the original order. So a file transfer application, for example, in that top layer for file, actually does not care what order the chunks of file data are delivered, because the retransmission or the strict in order are costly, and also they are being reassembled back into the original order in the first place. As an alternative to the overhead of reliable in-order delivery implemented within the network, a different type of service called best effort delivery was adopted by frame relay and internet protocol. So because of that, they don't want the cost of that strict or overhead of that strict in order and retransmission reliability within the network. A different type of service called best effort was adopted. So with best effort delivery, the network does not expend much effort to ensure that data is delivered without errors or gaps. Certain types of errors are usually detected using error detecting codes or checksums. So they use an error detecting code which is checksum, and they also do not expend much effort to ensure that all data is without error. So these checksum, such as those that might affect where a diagram is directed, but when such errors are detected, the errant diagram is merely discarded without further action. So they use this error detecting code for the error that actually matters, such as the area where a diagram is directed, because that will affect how it will be sent. If it doesn't have the address it is directing to, therefore it won't have the it is better discarded. So there is a priority that allows this to avoid the overhead of retransmission every little error. So that errant datagram for that specific error are merely discarded without further action. If best effort delivery is successful, a fast sender can produce information at a rate that exceeds the receiver's ability to consume it. So because you're sending it fast, because you're not using as much overhead or expending energy in retransmitting or making every data reliable, you could send a lot of data at a short period of time that your receiver can consume it. In best effort IP networks, slowing down a sender is achieved by flow control mechanisms that operate outside the network. So because of this, in this type of service, that sending of data is being slowed outside the network or of a flow control mechanism. So it has a checksum to detect error. It also has a error control mechanism such as checksum. It also has a flow control mechanism outside the network. So the error control, it's still within the network, but the flow control is outside. So these flow control are at a higher levels of communication system, and TCP also handles this problem. It's a higher level of this layering, which we will discuss here, the OSI, and also handled by TCP protocol suite. This is consistent with end-to-end argument. TCP, which resides at the end host, handles rate control. So because this flow control are at the higher level or in the application level, it comes to one with the end-to-end argument, or it align with the end-to-end argument, which you can control it using the application instead of that lower level. But the feature is there. You can activate that in application, but it does not necessarily on the lower level. It also consistent with fate sharing. The approach allows some elements of the network infrastructure to fail without necessarily affecting the ability of the devices outside the network to communicate. So it also align with fate sharing, which if this gets broken or one network gets broken, it doesn't matter because it will not affect the entire system as long as some communication path continues to operate, because that remains open. So again, fate sharing is what allows you the connection of TCP to remain open even the connection or internet connection suddenly stop. Design and implementation. Although a protocol architecture may suggest a certain approach to implementation, it usually does not include a mandate. Consequently, we make a distinction between the protocol architecture and implementation architecture, which defines how the concept in a protocol architecture may be rendered into existence, usually in the form of software. So we differentiate the design principles with the actual implementation on our specific context, because again, design is an art more than it is science. It's different in different contexts, and it's usually in the form of software. Many of the individuals responsible for implementing the protocols for the ARPANET were familiar with software structuring of operating systems. So they know how the operating systems works. Therefore, they learn from it. And an influential paper describing the multi-programming system advocated the use of hierarchical structure as a way to deal with verification of the logical soundness and correctness of a large software implementation. So because of that, they get some ideas with principles that has worked in the past, and they also differentiate that from the implementation. They learn from the OS, also they learn from multi-programming paper that I advocate the hierarchical structure as a will as a way to deal with verification of the logical soundness and correctness of large software implementation. So usually a logical structure, a layering structure are used to verify correctness of large software implementation. They learn from it. That's also the reason for abstraction on every layer. Ultimately, this contributed to a design philosophy for networking protocols involving multiple layers of implementation and design. This approach is now called layering and is the usual approach to implementing protocol suites. So now this is the has become the design philosophy from multiple sources. First from principle, implementation, operating system, and this multi-programming. So this has become where the knowledge or the design of the networking protocols came from, involving multiple layers of implementation and design. So again, it came from implementation and design. This approach is now called layering and is the usual approach to implementing protocol suites. So to understand the TCP/IP, you need to understand this layering of software. That is the design philosophy that people who created this. Layering, with layering, each layer is responsible for a different facet of the communication. Layers are beneficial because a layered design allows the developers to evolve different portions of the system separately. Often by different people with somewhat different areas of expertise, essentially allowing abstraction and specialization benefit to come to fruition. So here is the standard 7-layer OSI model as specified by the ISO. Not all protocols are implemented by every network device, at least in theory. The OSI terminology and layer numbers are widely used. The application specify methods for accomplishing some user-initiated task. Let's start with physical. It specify connectors, data rates, and how bits are encoded on some media. So the data rates is here, how the data would come out from your physical Ethernet. Also describe low-level error detection and correction. So it also provides the error detection plus frequency assignments. That's also the reason why some Ethernet just is faster than others, because they use this higher level physical. So when you connect it to your Wi-Fi, a higher level physical or Ethernet, it would just work faster. Examples include V92 Ethernet 1000 BST SONET/SDH. So although the OSI model suggests that 7 logical layers may be desirable for modularity of a protocol architecture implementation, the TCP or IP architecture is normally considered to consist of 5. People think that the OSI model is the way network works, but in reality, it's actually TCP or IP. And again, the implementation depends on different applications. So TCP/IP, which we will later discuss, more accurately depict how our real-world networks work. There was much debate about relative benefits and deficiencies of the OSI model and the ARPANET model that preceded it. During the early 1970s, although it may be fair to say that TCP or IP ultimately won, a number of ideas and even entire protocols from the ISO protocol suite, protocols standardized by ISO that follow the OSI model, have been adapted for use with TCP or IP. So this is the evolution of the network model. It started from ARPANET and then the OSI model and then the TCP IP. Obviously the TCP IP ones, but they got a lot or learned from, copy a lot from the layer that works from OSI or from those generated by ISO. As described briefly in figure 1.2, each layer has different responsibility. From the bottom up, the physical layer defines methods for moving digital information across a communication medium such as a phone line or fiber optic cable. So this physical layer, they define the method for moving digital information across a communication medium. So this communication medium are a phone line or fiber optic cable. Portions of the Ethernet and wireless LAN Wi-Fi standards are here, although we do not delve into this layer very much in this course. So that's the physical, that's the first. The link, so it specifies method for communication across a single link, including media access control protocols when multiple systems share the same media. So a media access control is when control protocol is when multiple systems share the same media. Error detection is commonly included at this layer along with link layer address formats like Ethernet, Wi-Fi, ISO. So the link or data link layer includes those protocols and methods for establishing connectivity to a neighbor sharing the same medium. Kind of like a media access control. But here, doesn't need to be media access control. Some link layer networks like DSL connect only two neighbors. When more than one neighbor can access the same shared network, the network is said to be multi-access network. Wi-Fi and Ethernet are examples of such multi-access link layer networks because more than one neighbor, not just two, which is DSL, connect only two neighbors that form, a link that connect them. Here, you could have multiple neighbors for Wi-Fi and Ethernet. So these are examples of such multi-access link layer networks, and specified protocols are used to mediate which stations have access to shared medium at any given time. Again, and specific protocols are used to mediate which stations have access to shared medium at any given time. So these protocols will determine people that can access the Wi-Fi. For example, the password, they are your internet provider at any given time. So the protocol will determine that, and later we will discover how those protocols abstract away from others, kind of like encapsulating it deeper and deeper to the TCP or IP protocol. So moving the layer stack, the network or inter-network layer is of great interest to us. For packet networks such as TCP or IP, it provides an interoperable packet format that can use different types of link layer networks for connectivity. So we will discuss this layer a lot. It specifies methods for communicating in a multi-hop fashion across potentially different types of linked networks. So it's this kind of basically what allows the internet, because it allows you to have the packet in case to other network or switch in case one gets down, and it support a different types of link layer below. For packet networks, describe an abstract packet format, and it for packet networks, it describes an abstract packet format and its standard addressing structure, which is datagram, X.25, PLP, ISO, CLNP. So those are the example of this network. It specifies the beginning and the end address, commonly an IP datagram or IP address. The layer also includes an addressing scheme for host and routing algorithms that choose where packets go when sent from one machine to another. So this layer has the algorithm in it that choose where packets go when sent from one machine to another in case the packet or the switch to other um, to that supposedly where that packet goes went down. So this is where the algorithm are inside, or this is the layer where the that algorithm will go. So the addressing scheme or the format, it specifies that format as well. Above layer 3, we find protocols that are, at least in theory, implemented only by end host, including the transport layer. So in theory, anything above here are abstracted from the lower down. These define all the abstraction in the network that allows us to send um, from one network to another. So this is kind of how we solve that multiple networks problem we discussed earlier. So here transport, it could be implemented or could be activated or deactivated by the programmer or the application. So it specifies method for connections or associations between multiple programs running on the same computer system. This layer may also implement reliable delivery if not implemented elsewhere, like Internet TCP, ISO TP4. So you can implement a TCP. This is where you implement a TCP or UDP in the transport layer. You can choose if you want a reliable or not. So that again is implemented by host. Also of great interest to us, it provides a flow of data between sessions and can be quite complex depending on the types of service it provides, like reliable delivery on a packet network that might drop data. Specifies methods for connections or associations between multiple programs running on the same computer system. This layer may also implement reliable delivery if not implemented elsewhere, like Internet TCP. Sessions represents ongoing interactions between applications. So between applications in that same network or in other networks, this is how you configure the cookies. Like when cookies are used with web browser during web login session. And session layer protocols, MIP, so it uses session layer protocols to achieve this or to be configured by the end host. And session layer protocols may provide capabilities such as connection, initiation, and restart. So this protocol could also start the connection, and it could also restart it. That's the reason why it provides the cookies, because it can use a timeout to be able to disregard that cookies, plus checkpointing, saving work that has been accomplished so far. This is also where you put the cache, saving the work that has been accomplished so far in the client side's web app. Above the session layer, we find the presentation layer, which is responsible for format conversions and standard encodings for information. So let's just read this the session. It specifies method for multiple connections constituting uh, constituting a communication session. This may include closing connections, restarting connections, and checkpoint progress. ISO X225 is a session layer protocol. So 1X25 that came from ISO uh, has also a session layer protocol called ISO X.225. Presentation, it specifies methods for expressing data formats and translations. Rules for application. So this is where the protocol that specify how the application would receive the data. Could be JSON format, XML, etc. A standard example would be conversion of EBCDIC to ASC2 coding for characters, but of little concern today. Encryption is sometimes associated with this layer, but can also be found at other layers. So because because you express data format and you convert this to other type of data, you could implement encryption here. Let's say you have this as a web server, you encrypt this by um, changing it to a different characters, etc. Now the application specifies method for accomplishing some user initiated task. So for example, application layer protocols tend to be devised and implemented by application developers. Example include FTP, Skype, etc. So these are the front-end level protocol. Includes FTP. So those are the protocol. Depending if your application are accepting or will gonna accept files, and if your um, application has a database to support that. Above the session layer, we find the presentation layer, which is responsible for format conversions and standard encodings for information. As we shall see, the internet protocols do not include a formal session or presentation protocol layer. So these functions are implemented by application if needed. So internet um, protocols, which we're gonna discuss next, do not include this presentation layer because it's up to the end host to implement it. And the encryption, as I've said, could be implemented on other protocol instead of this, or another layer rather. But each layer has protocol, so it could mean the same thing. The top layer is the application layer. Application usually implement their own application layer protocols depending on their support, like FTP for files, XML, HTML, FTP, Skype, etc. for UDP connection, and these are the one most visible to users. There's a wide variety of application layer protocols, and programmers are constantly inventing new ones. Consequently, the application layer is where is the greatest amount of innovation and where new capabilities are developed and deployed. Multiplexing, the multiplexing and encapsulation in layered implementations. So how do we encapsulate, decapsulate, multiplex, and demultiplex in this implementation? One of the major benefits of a layered architecture is its natural ability to perform protocol multiplexing. This form of multiplexing allows multiple different protocols to coexist on the same infrastructure. So because of this layer implementation, there's a complexity in which different protocols coexist in the same infrastructure or in the same network. As you can see, we have FTP, we have presentation protocol, etc. Right? Physical link protocol. So there's a different way or set of behaviors to communicate that forms this protocol suite. So it also allows multiple instantations of the same protocol object. So aside from multiplexing or allowing multiple different protocols to coexist on the same infrastructure, it also allowed to instantiate this same protocol object on that layer to be used simultaneously without being confused. That's kind of how we achieve multiplex utilization that allows multiple networks to coexist without having unreliable network, at the same time having same activity run on the network concurrently. Multiplexing can occur at different layers and at each layer a different sort of identifier is used for determining which protocol or stream of information belongs together. So multiplexing can occur at different layers and at each layer a different sort of identifier is used for determining which protocol or stream of information belong together. So in each layer a different protocol could coexist. At the same time, each layer has a sort of identifier to be able to do this encapsulation and decapsulation in determining which protocol or stream of information belong together. So this sort of identifier are used to be able to distinguish protocol or a stream of information that belong together to not be confused when you're sending packet or you're sending data from your computer to the internet. For example, at link layer, most link technologies such as Ethernet and Wi-Fi include the protocol identifier field value in each packet to indicate which protocol is being carried in the link layer frame. IP is one such protocol. So this, for example, a Wi-Fi actually have an identifier field value like IP in each packet to indicate which protocol is being carried in the link layer to transfer therefore to another computer on the network. When an object or packet, message, etc. called a protocol data unit at one layer is carried by a lower layer, it is said to be encapsulated as opaque data by the next layer. So, meaning when your packet or object are going down to down the layer, it is said to be encapsulated as opaque data by the next layer. So the next layer are encapsulating it by a header or kind of a trailer to be able to add data to it to distinguish that to be able to be used to decapsulate it later. Thus, multiple objects at layer n can be multiplexed together using encapsulation in layer n-1. So the way to multiplex multiple objects or instantiation of this protocol in each layer is to encapsulate it by additional header or trailer to distinguish it from other protocol or from lower, above, or below when encapsulating or decapsulating. Encapsulation is usually used in conjunction with layering. So without layering, you don't actually have encapsulation, because this is the entire usefulness in of this, in at least in networks. Pure encapsulation involves taking the PDU of one layer and treating it as opaque. So a packet or a message or an object instantiation involves taking the PDU of one layer, like the layer above or below, the layer below or above, and treating it as opaque or uninterrupted data by adding like header or trailer at the layer below. Encapsulation takes place at each sender, and decapsulation, the reverse operation, takes place at each receiver. So the packet are being encapsulated at each sender, and the packet are being decapsulated at each receiver. Most protocols use headers during encapsulation. A few also use trailers. So most of this protocol that is being instantiate a PDU or a packet at first, right, and then a PDU for each layer, use header during encapsulation. The identifier at layer n-1 is used to determine the correct receiving protocol or program at layer n during the multiplexing. So again, the identifier at layer n-1, or those header or trailer, used to determine the correct receiving protocol or program at layer n during the multiplexing. So that identifier or header are used by that receiving protocol during the multiplexing. So in figure 1.3, each layer has its own concept of a message object or a PDU corresponding to a particular layer responsible for creating it. Of course, each layer has its own encapsulation or identifier for each of these. So they have a own concept of a message object, a PDU. So that's what a PDU, a message object corresponding to that particular layer, that distinguish or identify that layer to be able to be used for receiver for the multiplexing or decapsulating, and to be used by sender for encapsulating. For example, if a layer 4 transport protocol produces a packet, for example, if a layer 4 transport protocol produces a packet or instantiate an object or packet, it would probably be called a layer for PDU or transport PDU to distinguish that at that layer. When a layer is provided a PDU from the layer above it, it usually promises to not look into the contents of the PDU. That's another property, is you can't look on that PDU. That maintains the integrity across this network or internet. This is what makes it safe. This is the essence of encapsulation. Each layer treats the data from above as opaque and interruptible information. Most commonly, a layer prevents the CBU, PDU of the one above or below with its own header. Although trailers are used by some protocols, not TCP or IP. So TCP or IP does not use trailer, only header. The header is used for multiplexing data when sending and for the receiver to perform demultiplexing based on a demultiplexing demux identifier. So the sender use header for multiplexing. For demultiplexing, it used the demux identifier. So it's kind of like another identifier to be able to demultiplex it instead of trailer, right? It's kind of connected to that header, but not really. We call that demux identifier. So figure 1.3, encapsulation is usually used in conjunction with layering. Again, pure encapsulation involves taking the PDU of one layer, because every layer has PDU, taking that and treating it as opaque or uninterrupted data the layer below, because without that integrity, you cannot call that encapsulation. Encapsulation takes place at each sender, and decapsulation, there is a reverse operation, takes place at each receiver. Most protocols use header during encapsulation. A few also use trailers. In TCP or IP networks, such identifiers are commonly hardware addresses, IP addresses, and port numbers. So the hardware address are for the physical part or physical layer, near the physical layer. IP address definitely near the link layer, and port numbers in the TCP part, or in the um, I would guess it's at the application um, or end host managed part. So here's an example. We will discuss the details of that later, but that's just my guess. The header may also include important state information, such as whether a virtual circuit is being set up or has already completed set it set up. So it's like the header or the per flow state we discussed in the previous video, in which for virtual circuit, the first kind of like the first networks or design is you initiate a per flow connection, which is a lot of overhead. So here you kind of have the same context. You initiate the per flow, but at the same time you put a state in the index table after that to be able to read or remember the state. Here it's kind of like it get that good idea from that previous um, design. Now the header contains the state, whether the virtual circuit is being set up or has already completed setup. the resulting object is another PDU. So when you attach a header on that with that state is another PDU. So whether uh, it changes from complete or whether it change from set up, the resulting encapsulation of that is another PDU that can be used by another layer for encapsulation and decapsulation. One other important feature of layering suggested by figure 1.2 is that in pure layering, not all network devices need to implement all the layers. Figure 1.2 here, the OSI, so it's talking about OSI, is that in pure layer one other important features of layering suggested by 1.2 is that pure layering not all network that in pure layering not all network devices need to implement all layers. So the good important feature is its modularity, because not all the devices in the network needs to implement all the protocols or all the layers in the OSI model. Figure 1.4 here shows that in some cases a device needs to implement only a few layers. It is expected to perform only certain types of processing. So here, for example, a switch, it only activates the link and physical layer. For router, it only activates network, link, and physical layer, while the other end host has application, presentation, session layer because it activates that, it needed that for that context. Now, different network devices implement different subsets of the protocol stack. And hosts tend to implement all the layers. So end hosts usually implement all the layers because they need to be connected to the front end user, unlike the lower level which is hidden from the user. Routers implement layers below the transport layer, and switches implement link layer, protocol, and below. This idealized structure is often violated because routers and switches usually include the ability to act as a host. Now, this may explain what we're trying to pertain, that the other network device such as switch or router does not necessarily need to implement the application, but in modern times we actually have application because the router or switch needs to be managed via web application. So because routers and switches usually include the ability to act as a host, like to be managed and set up. So just wanting to be host or to be set up or managed includes you needing to implement that top layer or that protocol at the top, and therefore need an implementation of all the layers even if they are rarely used. In figure 1.4, somewhat idealized small internet includes two end systems, a switch and a router. In this figure, each number corresponds to a type of protocol of a particular layer. So this number 1, 2, 3, 4, 5, 5 to 7 indicates or corresponds to a type of protocol, whether it's link layer, whether it's link protocol, physical protocol, etc. As we can see, each device implements a different subset of the layer stack. The host on the left implements three different link layer protocols, D, E, and F. So these two indicates indicates a protocol type, while this indicates the difference of a protocol. Link layer F is obviously different from link layer E and link layer D. The host on the left implements three different link layer protocols, not layer protocol type, D, E, and F, with corresponding physical layers and three different transport layer protocols. That run on a single type of network layer protocol. So here we have a three transport layer protocol ABC. So here the reason why it says a single type of network layer protocol is because a network layer we don't have other type. And hosts implement all the layers. Switches implement up to layer 2. This switch implements DNG protocol. And routers implement up to layer 3. So until network layer. Routers are capable of interconnecting different types of link layer networks. So routers could implement a different type of link layer networks like this link layer G and D. A switch as well, right? And must implement the link layer protocols for each of the network types they interconnect. So the routers, of course, should be able to use the same type of layer for interconnecting different type of link layer protocols. The Internet of Figure 1.4 is somewhat idealized because today's switches and routers often implement more than the protocols they are absolutely required to implement for forwarding data. This is for a number of reasons, including management. In such circumstances, devices such as routers and switches must sometimes act as host and support services such as remote login. To do this, they usually must implement transport and application protocols. So to be able to access your internet or configure that, they must implement a transport and application protocols. So now you know if you're accessing your internet provider web app to configure that, you're actually that actually needs an activation of transport and application protocol. So of course, different type of different protocol could be used, but mostly that's TCP. Um, I don't know what type or what specific protocol for transport and application are being used, but definitely needs to activate that to be able to create that web application. Although we show only two hosts communicating, the link and physical layer networks labeled as DNG might have multiple hosts attached. So we only show two, but it could have multiple hosts. The link and physical layer networks might have multiple hosts attached. If so, then communication is possible between any pair of systems that implement the appropriate higher level protocols. So if you have other host that implements the higher level, the right higher level that connects all the way to uh, all the way down, as long as you have Wi-Fi, basically you're able to connect in this network. If this network are also using the Wi-Fi in there, what protocol layer is that? I think it's a link layer in OSI model. Let's check again. Yeah, it's in link layer. In figure 1.4, we can differentiate between an end system. Oh my god, I think we repeat this. We repeated. So here we stop here. If so, then communication is possible between any pairs of systems that implement the appropriate higher level layer protocols. In figure 1.4, we can differentiate between an end system, the two hosts on either side, and an intermediate system. So these are the end system, the two hosts on the other hand, and the intermediate system, the router in the middle for a particular protocol suite. So we can also describe this or differentiate this as a two host with an intermediary of one router. Layers above the network layer use end-to-end protocols. So end-to-end, again, it helps to configure it at the end host instead of the lower level. So it follows that design principles. In our picture, these layers are needed only on the end systems. The network layer, however, provides a hop-by-hop protocol and is used on the two end systems and every intermediate system. So this network layer use a hop by hop. As you can see, you connect to this layer and here. That's what we call a hop by hop layer. It's not a link layer F protocol. It's not a link layer E, but a hop by hop protocol, and is used on the two end systems and every intermediate systems. As you can see, it didn't connect with switch because it's not an intermediate. So that's the use of a network here for two hosts and intermediate system. It provides a hop-by-hop protocol. The switch or bridge is not ordinarily considered an intermediate system because it is not addressed using internetworking protocols addressing format, and it operates in a fashion that is largely transparent to the network layer protocol. So because switch is not addressed using this internetworking protocol, which is the hop-by-hop protocol, and it operates in a fashion that is largely transparent to the network layer protocol, which means it doesn't actually need to use that. It is not considered an intermediate system. From the point of view of routers and end systems, the switch or bridge is essentially invisible. So as you can see, it didn't connect. It can only see the network layer. Rows at the bottom, it's all in the physical side, the cable connected underground, etc. A router by definition has two or more network interfaces because it connects two or more networks. So because this router has a network layer that could provide connection to uh, more hosts, it is not just a two host network, but rather um, multi-network. No, it could basically provide interface to multiple end hosts. Any system with multiple interfaces is called multi-home. So that's what you call this, multi-home. Any network layer that provides multiple interfaces is called multi-home. Multiple interfaces for multiple users. A host can also be multi-home, but unless it specifically forward packets from one interface to another, it is not called a router. So you can also activate a multi-home in the network layer of this end host, but unless it forward packets around the network, it is not called a router. Also, routers need not be special hardware boxes that only move packets around an internet. So this device does not necessarily need to be a router or a specialized router. Most TCP or IP implementations, for example, allow a multi-home host to act as a router also. So most of TCP or IP implementation nowadays allows n host or like this to activate the network layer to route packets through the network. Also, if properly configured, multi home host to act as a router. Also, if properly configured to do so, but you need to properly configure it. Again, to access the advanced function from the end host provided by this protocol suite, you need to provide or expend more time for configuration. In this case, we can call the system either a host when an application such as file transfer protocol or the web is used. So in this case, the end host could serve as dual purpose. It could either be a host if I use a file transfer protocol to activate this, but we can call that a router as well if it's being used to forward packets from one network to another. Again, the network does not uh, is not limited to an end host connected to it. It could be another network from another city, from another geography. One of the goals of an internet is to hide all of the details of the physical layout, the topology, and lower layer protocol, which makes kind of make the switch invisible earlier, and lower layer protocol heterogeneity from the applications. Although this is not obvious from our two-network internet in figure 1.4, the application layer should not care and do not care, which makes the, again, it follows the end-to-end um, design, end-to-end frame. So it shall not care on the lower levels that even though each host is attached to a network using link layer protocol like Ethernet. So although each host, where am I? So even though each host, right, is connected using that link layer protocol or the IP address or Wi-Fi, uh, it does not mean uh, that it is aware on the application above, because that's the essence of encapsulation we discussed earlier. The data is uninterrupted along the communication path. Even though each host is attached to a network using link layer protocol like Ethernet, the hosts are separated by a router. So like Ethernet, yeah. So the Ethernet connected that. It could be Wi-Fi as well. The hosts are separated by a router and switch that use link layer G. There could be 20 routers between the host with additional types of physical interconnections like link and physical, and the applications would run without modification, although the performance might be somewhat different. That's how you get the speed of the Wi-Fi up, because it's just more connected, or has direct connection in the link and physical layer. Abstracting the details in this way is what makes the concept of an internet so powerful and useful. The architecture and protocols of the TCP or IP suite. So far, we have discussed architecture, protocols, protocol suites, and implementation techniques in the abstract. So we discussed the architecture design, the protocols, a set of behaviors for a common language, a protocol suite, a set of protocols, and implementation in each use of these network devices in the abstract. In this section, we discussed the architecture, in particular protocols that constitute the TCP or IP suite. So what are the actual protocols and the architecture of TCP or IP suite? So figure 1.5 depicts the layering inside inspired by ARPANET reference model. So again, we get some design principle with the evolution of TCP or IP suite, which was ultimately adopted by TCP or IP suite. So this won the game again. The structure is simpler than the OSI model, but real implementation include a few specialized protocols that do not fit cleanly into the conventional layers of the ARPANET and OSI model. Figure 1.5, protocol layering based on the ARM or TCP or IP suite used in the internet. There are no official session or presentation layers. In addition, there are several adjunct or helper protocols that do not fit well into the standard layers yet perform critical functions. Again, that's a keyword, functions, for the operation of other protocols. Some of these protocols are not used with IPv6, like IGMP and ARP. So these network adjunct, some of these protocols are not used with IPv6, like IGMP or ARP. So here IGMP. Starting from the bottom again, from figure 1.5, working our way up the stack, the first layer we see is 2.5, an official layer. There are several protocols that operate here, but one of the oldest and most important is called the address resolution protocol. So these are the most important and the oldest with TCP IP, the address resolution protocol. So unofficial layer used to map addresses used at the network to those used at the link layer. On multi-access link layer networks. So let's go back. What are the multi-access link layer? Here. So Wi-Fi and Ethernet are example of such multi-access link layer. So when more than one neighbor can access the same shared network, The network is said to be a multi-access network. So one or more network can access this same shared network. So a lot, two, three or more, uh, two or more of you can communicate in this network. It is called a multi-access link layer. So here, uh, there are several protocols, which is the address resolution protocol. Unofficial layer used to map addresses used at the network to those used at link layer. So before we have a physical address here, now we have link to network. I mean, we only have link connected to network. So this is because this part 2.5 to 3, we map addresses used at the network to link and link to network, like an ARP or address resolution protocol. So we essentially convert that Wi-Fi data to a network, which is an IP address. So it is a specialized protocol used with IPv4 and only with multi-access link layer protocols such as Ethernet and Wi-Fi. So again, Wi-Fi is actually a protocol to convert between the addresses used by the IP layer and the addresses used by the link layer. So the IP layer, to be able to convert that to a link layer, such as one that can read by the Wi-Fi, it adds header into it. And then the Wi-Fi link that to other shared network, because that's a multi-access link layer protocol. So we examined this protocol in chapter 4 more fully, but basically ARP are used for address resolution protocol or for mapping that. In IPv6, the address mapping function is part of ICMP-v6. So instead of ARP, it used the ICMP-v6, which we discussed in chapter 8. At layer number 3 in figure 1.5, we find IP, the main network layer protocol for the TCP IP suite. So IP is actually the main layer for TCP IP suite. We discussed it in detail in chapter 5. So here, it defines abstract datagrams and provides routing. So this IP provides the abstract datagram that defines the beginning and end address. Example include IP 32-bit address, 64 kilobytes maximum size. So it's kind of provides that metadata as well to be able to distinguish that with IPv4 and IPv6. 128-bit address up to 4 gig maximum size. The PDU that IP sends to link layer protocol is an IP datagram. So the PDU, or the object instantiated by this protocol to this link, is called an IP datagram and may be as large as 64 kilobytes and up to 4 gigabytes for IPv6. Again, it may be as large as that. Basically, that's the upper bound, the 64 kilobytes and 4 gigabytes for IPv4 and IPv6. In many cases, we shall use the simpler term packet to mean an IP datagram when the usage context is clear. Fitting large packets into link layer PDUs called frames that may be smaller is handled by a function called fragmentation. So if you fit a large packet, whether from network adjunct, those that doesn't fit with the OSI to network, or from link to adjunct, fitting that or converting that large packets into a smaller one uh, is handled by a function called fragmentation that may be performed by IP host. So an IP host performs that which is on the network layer itself. So an IP host, again, an end host could be could be activate its IP or network or IP protocol and be able to execute this fragmentation in its network layer, and some routers when necessary. So it could be performed by a host or some routers when necessary. Um, if the packets are too large and you're using IPv4, and remember it only has 64 kilobytes, it must have a fragmentation function provided by that IP host or the router. In fragmentation, portions of large datagram are sent in multiple smaller datagrams called fragments. This is what people may have usually think or usually um, imagine when data are being divided across the networks. It's only in this part in network or IP protocol, network layer and IP protocol. In fragmentation, portions of a larger datagrams are sent in multiple smaller datagrams called fragments. So that smaller datagrams, when has been chopped using fragmentation, it is called fragments, and put back together called reassembly when reaching the destination, whether it's in link adjunct, network adjunct, or transport layer. We discussed fragmentation in chapter 10. When discussing architecture, the details of IPv4 versus IPv6 matter little when we delve into the way particular addressing and configuration. So when we delve into address, which is the IP, and the configuration, such as that fragmentation, or with the ARP, right, in the link part or link layer, the distinguish or difference work. Chapter 2 and chapter 2, for example, these details will become more important, those link and in the network layer. Because IP packets are datagrams, each one contains the address of the layer 3. Sender and recipient. So the layer 3, which each IP packets contains the address of layer 3 of its sender and the recipient. So the sender address on its IP layer and the recipient address on its IP, kind of like the address of that IP layer, to be able to unpack or encapsulate and decapsulate it properly. These addresses are called IP addresses and are 32 bits long for IPv4 because it saves that sender and recipient address for the um, source and target. Let's call it source and target host for IP, and 128 bits for long for IPv6. So we discussed them in detail in chapter 2. The difference in IP address size is the characteristic that most differentiate IPv4 from IPv6. So it's their size that most distinguish them, because 128 bit for IPv6 and 32 bits for IPv4. The destination address of each datagram is used to determine which each datagram should be sent. So the destination address put into that link layer and the IP protocol or IP packet. Sorry, it's not the same. IP protocol, in that IP protocol, using an IP packet to determine where each datagram should be sent. And the process of making this determination and sending the datagram to its next hop is called forwarding. So, though it may be implemented by an IP host, but the process of sending that to that using that IP address with a sender and recipient address is called forwarding. It may not be forwarding packet, but the process of sending that datagram to that layer or to the other end host layer is called forwarding. So again, the reason we have that distinction is because of the router. We only call an IPN host router if it forward packet, right? If it actually has to worry about transferring data, because usually it's hidden from the top. Both routers and hosts perform forwarding, although routers tend to do it much more often. So routers and hosts do both forwarding, but routers do it more often because that's its center job. There are three types of IP addresses, and so let me unpack this. So earlier we described an IPN host to be only called router if it forward packets to other networks. So the key is to other networks. But both that forward packet or forward datagram, both forward datagram and routers just do it more often. There are three types of IP addresses, and the type affects how forwarding is performed. Unicast, destined for a single host; broadcast, destined for all hosts on a given network; and multicast, destined for a set of hosts that belong to a multicast group. Chapter 2 looks at the types of addresses used with IP in more detail. So in that link layer, in that network layer, there are three types of addresses in that IP protocol that affects how it forwards the packet or datagram to the recipient. A unicast for only a single host; broadcast, destined for all hosts on a given network; and a multicast, destined for a set of hosts that belong to a multicast group. So basically you're targeting a set of hosts instead of all hosts and instead of a single host. Chapter 2 looks at the type of addresses used with IP in more detail. The Internet Controlled Message Protocol (ICMP) is an adjunct to IP, and we label it as Layer 3.5 protocol. It is used by the IP layer to exchange error messages and other vital information with IP layer in another host or router. So let's say this network layer wants to find error from another host it's connecting. We use this 3.5. So an official layer that helps accomplish setup, management, and security for the network layer. So it is the also help with the setup of security. Example: ICMP and IGMP, IPsec in chapter 18. So again, ICMP specifically are used by IP layer to exchange error message and other vital information from other or from recipient IP datagram or IP protocol. There are two versions of ICMP: ICP MPv4 used with IPv4 and ICMPv6 and used with IPv6. ICMPv6 is considered considerably more complex and includes functions such as address auto-configuration and neighbor discovery that are handled by other protocols like ARP on its adjunct link layer on IPv4 network. So although ICMP is used primarily by IP, it is also possible for applications to use it. Though this protocol are primarily or most frequently used by IP, it can also be used by application layer. Indeed, you will see that two popular diagnostic tools like ping and traceroute use ICMP. ICMP messages are encapsulated within IP datagrams in the same way transport layers PDUs are. So this ICMP, of course, it's in a IP diagram, IP layer. It is encapsulated with IP datagrams in the same way transport layer PDUs are. So even if you're sending message in the point of view of IP layer or application layer, it is encapsulated with IP datagram. So that's what it means by in the same way transport layer PDUs are, because transport layer more like an application side. So the Internet Group Management Protocol IGMP also still network layer, adjunct layer. So the Internet Group Management Protocol is another protocol adjunct to IPv4. So again, it is adjunct to the IPv4 network or IP network layer IP protocol. It is used with multicast addressing and delivery to manage which hosts are member of a multicast group. So it is used to determine which host is a member in a multicast group, a group of receivers interested in receiving a traffic for a particular multicast destination address. So of course, this being used for specific purposes where you want to send a message for a specific set of people in the specific or in a multicast group that wants to receive your message. We describe the general properties of broadcasting and multicasting along with IGMP and multicast listener discovery protocol MLD used with IPv6 in chapter 9. At layer 4, the most common internet transport protocols are vastly different. So here we have more protocols, more variation of protocols because it's more on application side. The most widely used, the transmission control protocols, deals with problems such as packet loss, duplication, and reordering that are not repaired by the IP layer. So usually an IP layer does not repair a packet loss or a duplication and reordering. This is where the transport layer or at layer 4 comes in, because it allows for transmission in case some packet is lost, or deletion in case it's duplicate, or reordering in case it's unordered. It operates in a connection-oriented VC fashion and does not preserve message boundaries. So the message boundaries, like we discussed in the previous video, it does not copy the how it is far or offsetted from other bytes sent from that same network or sent from the receiver or from the sender rather. Basically, it converts that to packet. It converts on its own. So that's what makes it that's what makes it TCP, and that's what make it deal with packet loss, duplication, and reordering. TCP provides a reliable flow of data between two hosts. So because it's avoid packet loss and it reorder, it provides a reliable flow of data between those two IP layers because it ensures no packet loss. This is also the reason why we don't have that packet loss and we were able to um, um, send all the data using this transport or layer 4 protocol. It is concerned with things such as dividing the data passed to it from application into appropriately sized chunks for network layer below. So for IPv4, that's 64 kilobytes. So this is more the application of that division that we discussed in our canonical example earlier. It divides that and then reorder it. Doesn't wait for others or doesn't uh, preserve message boundaries, but it makes sure that there's no packet loss, no duplicate, and there's no unordered packets. Into again, data fast to it from the application into appropriately sized chunk for the network layer below. Acknowledging received packets and setting timeouts to make certain the other end acknowledge packets that are sent. So it sent types out to be able to make sure that the other layer of the IP recipient address receive the packet we have sent. And because this reliable flow of data is provided by the transferred layer, the application layer can ignore all these details. So because it is implemented in layer 4, if you activate TCP in this layer 4, you automatically don't have to worry on and host on your application level protocol. The PDU that the TCP sends to IP is called a TCP segment. So again, it's a TCP segment. It is not a datagram, right? It calls TCP segment. User datagram protocol or UDP. So this is actually what UDP means. User datagram protocol. So it's still a datagram, but for TCP it's kind of different. Instead of TCP datagram, it's TCP segment called for the PDU. But the essence is still the same. They all came from the PDU or the packets basically. So user datagram protocol UDP provides little more than the features provided by IP. So it provides additional feature that provided by IP layer. UDP allows applications to send datagram that preserve message boundaries. So it allows the application at the top to send datagrams that preserve message boundaries to other hosts, but imposes no rate control or error control. But it poses no error control. It doesn't check packet loss or duplicate. It also doesn't reorder things. It also doesn't have rate control. So if you send more than kind of like the best effort delivery, you have some attachment outside that allows you to control that have you the flow control mechanism to control the flow of packets. UDP on the other hand provides a much simpler service to the application layer. It allows datagrams to descend from one host to another, but there's no guarantee that datagrams reach the other end. Any desired reliability must be added by the application layer. Indeed, about all that UDP provides is a set of port numbers for multiplexing and demultiplexing data, plus a data integrity checksum. So it only provides that error control, the checksum we provided in the previous example, for best effort delivery, and it allows port numbers for multiplexing or to be able to be instantiate by multiple of multiple protocol object at the same time to be able to connect to other networks simultaneously for multiplexing and demultiplexing data. So it uses a port number. So this is actually where you use a port number to connect to your application. There are two additional transport layer protocols that are relatively new and available on some systems. As they are not yet very widespread, we do not devote much discussion to them, but they are worth being aware of. The first is the datagram congestion control protocol. Specified in RFC 4340, it provides a type of service midway between TCP and UDP, connection oriented exchange of unreliable datagrams, but with congestion control. Congestion control comprises a number of techniques whereby a sender is limited to a sending rate in order to avoid overwhelming the network. So this congestion control consists of a different algorithm whereby the main concept is the sender is limited to a sending rate in order to avoid overwhelming the network. So it is a midway between TCP and UDP that it provides a connection oriented of unreliable datagrams. We discuss it in detail with respect to TCP in chapter 16. The other transport protocol available on some systems is called Stream Control Transmission Protocol, specified in RFC 4960. SCTP provides reliable delivery like TCP, but does not require the sequencing of data or the reordering feature of TCP to be strictly maintained. It also allows for multiple streams to logically be carried on the same connection and provides a message abstraction. So it's allow multiple streams to be logically be carried on the same connection. So meaning it is not limited to just one connection, but you can also it can also accommodate other connection as long as it has space for it, and provide a message abstraction which differ from TCP. SCTP was designed for carrying signaling messages on IP networks that resemble those used in the telephone network. So it's most usually a telephone network applied in the modern computing. So if you want to mimic that telephone networks, above the transport layer, the application layer handle the details of the particular application. There are many common applications that almost every implementation of TCP or IP provides. There's a lot of protocol in this layer that almost every implementation of TCP or IP provides. So all of implementation of this layering could use the many common application we use today. The application layer is concerned with the details of the application and not with the movement of data across the network. So it's more concerned on the logic of the front end or the front end and back end it provides to the user than on the network it connects to. The lower three layer are opposite. They know nothing about the application but handle all the communication details. So here it is. It's smaller, 2.53, 3.54, and 7. So these 3.5 are just the adjunct of network, and this link are also just an adjunct. So multiplexing, demultiplexing, and encapsulation in TCP or IP. We have already discussed the basics of protocol multiplexing, demultiplexing, and encapsulation. At each layer, there is an identifier that allows a receiving system to determine which protocol or data stream. So that's what we mean by stream. So when we said earlier that we can incorporate different stream in one connection, It means we're talking about the um, protocol connection or data stream belongs together. Usually there's also addressing information at each layer. The information is used to ensure that PDU has that the PDU has been delivered to the right place. So here's an example of that. DNS web server UDP IPv4 Ethernet. So the TCP or IP stack uses a combination of addressing information and protocol demultiplexing identifiers. So again, it uses an additional identifiers aside from the header to determine if a datagram has been received correctly. So that are actually the one used to make sure that it is received correctly. It also used for packet checking if it's packet loss, duplicate, or um, ordered. So the TCP or IP stack uses a combination of addressing information instead of a header. It's an addressing information now. And a protocol, the multiplexing identifiers. If a datagram has been received correctly, and if so, what entity should process it? So if so, what entity should process it, or what protocol and what endhost should receive it? Several layers also check numeric values like checksums, like that, one we copy or design features we copy from best effort delivery to ensure that the contents have not been damaged in transit. So that's how TCP make the avoid packet loss, duplication, and unordered datagram. Although it is not really part of the TCP or IP suite, we shall begin bottom up and mention how the multiplexing from the link layers perform using Ethernet as an example. We discussed several link layer protocols in Chapter 3. An arriving Ethernet frame contains a 488-bit destination address, also called a link layer or media access control address. So this is what you call MAC, which is 48-bit destination address. So let's imagine we're receiving some packets or datagram from other end host. So here it has a 48 destination where it will go, and a 16-bit field called the Ethernet type. So the Ethernet type is a 16-bit field, while the destination address is 48-bit. A value 0x800 hexadecimal indicates that the frame contains an IPv4 datagram. So if it's a 0x0800, it means that frame is an IPv4 datagram. Values of 0x0806 and 0x86DD indicates ARP and IPv6. So 0x086 is an ARP, the one we discussed with the link adjunct link layer for TCP, and 0x86DD for IPv6 respectively. Assuming that the destination address matches one of the receiving system's address, the frame is received and checked for errors. Again, assuming that the destination address matches one of the receiving system's address, the frame is received. So it will multiplex it as long as it checks, it tracks, it compares the receiving address with the destination address from that datagram and check for errors. It will also check for errors, and the Ethernet type field value is used to select which network layer protocol should process it. So you may think that Ethernet type are used to determine if it's a Ethernet link layer. It's actually used to be able to see what protocol above it, which is the network layer. And additionally, check for errors. in this demultiplexing. So that's how you check the errors. You don't just check errors when sending it, you also check errors when demultiplexing. Assuming that the received frame contains an IP datagram, so assuming that it has an IP datagram, the Ethernet header and trailer information is removed. So in this example, it has a trailer. So the Ethernet header and trailer information from that datagram is removed, and the remaining bytes, which constitute the frame's payload, are given to IP for processing. IP checks a number of items, including the destination IP address in the datagram. If the destination address matches some of its own and the datagram contains no errors in its headers, IP does not check its payload because again it's hidden. So for link layer, Ethernet, you're checking to network layer address. So the address inside it, or the address that it checked, is actually the network address. It's not the corresponding IP address because that's being checked in the network. So if the destination address matches one of its own and the datagram contains no errors, in its header, so it checks the error again. So aside from link layer that checks the error along this demultiplexing, an IP or network layer also checks an error in its header. So IP does not check its payload because it's hidden. So the 8-bit IPv4 protocol field called next header in IPv6 is checked to determine which protocol to invoke next. So the 8-bit, earlier we checked the 48-bit, now we're checking the 8-bit to check what to invoke in the next layer. Common values inside include 1 ICMP, 2 IGMP, 4 IPv4, 6 TCP, and 17 UDP. The value of 4 and 41, so we're getting to what? We're getting to now these ICMP, UDP, TCP, these are the transport layer. And next we're gonna demux on the port number for the actual application. So the value of 4 and 41, which indicates IPv6, is interesting because it indicates the possibility that an IP datagram may appear inside the payload area. So, which indicates IPv6 is interesting because it includes the possibility that an IP datagram may appear inside the payload area. So the value of 4 on that in that protocol from the previous layer, since we're already in the transport layer, which is actually the IPv4, and 41 indicates IPv6 is interesting because we're already in the transport. It indicates the possibility that an IP datagram may appear inside the payload area of an IP datagram. So an IP inside an IP datagram. So this violates the original concept of layering and encapsulation, but it is actually the basis for a powerful technique known as tunneling, which we use for VPN nowadays for secure communication. Once the network layer IPv4 or IPv6 determines that the incoming datagram is valid and the correct transport protocol has determined the resulting diagram reassembled from fragments if necessary is passed to the transport layer for processing. At transport layer, most protocols including TCP and UDP use port numbers for demultiplexing to the appropriate receiving application. Port numbers. Now, port numbers are 16-bit non-negative integers range. I think we'll have to continue this tomorrow.